So Leon Lederman, this guy from the Bronx, all these Nobel laureates came out of the Bronx. They were all, kids of plumbers and laundrymen in the case of Leon Lederman. And he wanted to call it the goddamn particle. And according to Sean's book, he said because of its villainous nature and the expense it is causing, this particle that we're going to be talking about today. And the title ended up being the God particle of this book that he wrote, which is why this term was foisted on us. So you might have heard in the popular press that there is this particle that they found, and it was the God particle, right? And it has all of this sort of metaphorical resonance. Well, it was supposed to be called the goddamn particle. And he said about the title of the book, he said the title ended up offending two groups: those who believe in God and those who do not. He said, we were warmly received by those in the middle. So we want to talk tonight about this particle. We won't refer to it as the God particle. I doubt we'll refer to it as the goddamn particle either. We really call it the Higgs particle. And it has this very important place in our understanding of the nature of matter. It was a sort of missing pin that we were waiting to discover to try to make this whole campaign of the past 50 years or more hold together. And so I was going to start with Sean, because Sean's a great expositor, and ask him to give us his take on what the Higgs is and what it does for us.
Well, it's a great story. Back in the 60s, even going back to the 1950s, physicists they thought they had more or less figured out electromagnetism, right? One of the fundamental forces of nature. And they had a great theory of gravity given to us by Einstein, general relativity. It didn't fit in with quantum mechanics, but it still is good enough to predict what the universe does. But there were these nuclear forces, these forces that were stuck inside the center of an atom, that did not extend out. And interestingly, they tried to invent theories of these forces, and they realized that the fact that the forces were stuck inside the nucleus, that they didn't fill the universe like electromagnetism or gravity, was a puzzle. It was hard to account for. It was difficult to sort of take the forces we knew about and generalize them to stick them in there. So a few young, bold physicists, theorists at the time independently came up with this idea. I know space all around us is filled with an invisible energy field that is absorbing the lines of force and making it short range, like a fog that fills the universe that is cutting off the light from all these different sources. And no one paid any attention to them whatsoever. And a few years later, Steven Weinberg said, well, if that is true, then I can explain everything. I can explain how all the weak interactions work and where particles get masses from. And no one paid any attention to him. And then a couple years after that, another brilliant physicist, Gerard de Toof, showed that it all made mathematical sense. And finally, the theorists started paying attention, and the experimentalists said, oh, this is good. We have something to look for. You're making a prediction. And several decades and several $1 billion later, we are writing books and having panel discussions about it.
So essentially you're saying we understand everything that there is to know about the matter forces once we find the Higgs.
What we call, imaginatively enough, the standard model of particle physics, it only made sense if you imagined that empty space is filled with this invisible energy field, which does sound bullshitty, right? It does sound like that doesn't sound like physics to me. What do you do to make it into physics? Well, you try to find it, you try to locate it, to test it, to get some data. And what that means is you poke at the field and you get it vibrating, and then those vibrations show up in our detector as a little track, which we call the Higgs boson. At least in theorists' imagination it does. The real Higgs boson decays long before you see any tracks. So we hand it over to the experimentalists to cleverly see what the Higgs decays into to guarantee that something like that was what we actually found.
Because theorists don't know how to poke, which is a deep comment. And they don't know how to shake or shimmy.
No, shimmying we do fine. We do fine.
So when you have a universe filled with vacuum and you want to make an excitation, you want something to happen, like a tornado, you have to figure out what to do. And the only way we could think about it, we didn't actually listen to the theorists very much. We just said, get as much energy in a tiny place as fast as possible, and maybe something will happen then. And so we don't even actually understand their equations. But we know how to shake shit.
Can I actually jump in here? Because one of my jobs is to parallel the discussion with sort of big picture stuff or the big brushstroke stuff. So one of the things that Sean and Melissa are distinguishing is the idea of a field. And we're used to electromagnetic fields. That's why your phones ping, because fields come through space and make your phone work, and they make they don't, they make other things work.
Until the power goes out.
Until the power goes out, right? Well, actually, our phones continue to work. But there's a distinction between a field that permeates all of space and a particle. So when we talk about the role of the Higgs field in elementary physics, it's the field that's important. It's this thing that permeates all of space. And you could say, well, why don't we look for the field? The field is very, very hard to look for, except in its most obvious way, which is that it seems to give us a sense of inertia as we move through it. But it's hard to perceive, it's hard to experimentally get a handle on that. And so what Melissa does is she goes and what did you say, you poke things? She shakes shit, and that's a technical term. It's an acronym. We'll tell you what it stands for later. And so she shakes the field. In principle, that's what we're doing, shaking the field, and that creates little particles. And those particles are the goal of things like the Large Hadron Collider, to find those particles. Would you say that that's crappy theorist talk?
No,
does that sound okay to you?
I really like theorists. I just trying to have fun. Because I know, isn't that a great feeling when your experiment goes down for 2 hours? It's a really interesting feeling. You feel at ease if you know it's going to come back up. So we knew the lights were going to come. Oh, they're coming back on, in case everybody's worried. So with the Large Hadron Collider, you build this tremendous experimental endeavor. Yeah, we built this huge thing I work with each experiment has 3,000 physicists and many more technicians and engineers and tiny people. Young people. Should I show one of those tiny people? You want to see, the Swiss are very small. That's very small. What is this that we're looking at? Oh, that's part of my experiment. These big things are the muon toroids. Toroids are magnetic fields. So when a muon particle, which can go through a lot of steel, goes through them, it bends slightly. And when it bends, we watch how much it bends, and we can tell how fast it's going. That's a big machine. Yeah, it's huge. That's only one of the many instruments. Did we decide we didn't know what this was? I thought I took that. That's a tracking chamber. When maybe 80 particles are made in each collision of 2 protons, and we track each particle that comes out, and we measure its momentum. We try and figure out what kind of guy it is, or girl. So just to give people a sense of scale, this is an accelerator where they're accelerating particles near the speed of light. It's 18 miles around, is that right? It's 27 kilometers. 27 kilometers, thank you. I'm more familiar with kilometers, too. And then they smash them together at an energy that is comparable to the energy of the universe a trillionth of a second after the Big Bang. So it's pretty hot. Sean, you had a good analogy.
They're moving at 99.999999% the speed of light.
Did you count the number of nines you just said?
I did. I know the one. I'm not going to lie to them that they paid good money to get here. That is the correct speed. And then they upgraded. I don't know. They might be moving faster now.
Remind me, compared to the temperature at the center of the sun,
I don't know. It's a lot of energy. What difference does it make? Like sometimes
it's a billion, Sean. It's
sometimes
a billion.
when I say the lifetime of the Higgs boson is 1 zeptosecond. And then I say, and that is, everyone's expecting me to say, 10 to the minus 21 seconds. Who cares how many seconds it is? It's a really short period of time. We can't actually see the little Higgs boson moving. The energies are really, really big. It's the highest energies we've ever created by ourselves here on Earth.
No, but you could say it's shorter than the length of time light needs to cross a proton. Proton is that little thing inside your knee.
There's one in every knee. What's this?
This is the accelerator. So in order to get the protons up to very, very high energies, they need to go around this 27-kilometer ring many, many times, and each time we kick them so that they go faster and faster. And so you need to have a round accelerator with these superconducting magnets. So magnets that are at 4 degrees Kelvin, which is, as Sean knows, is just low.
It's cold.
Cold. And these magnets have windings that have no resistance. So this is it. And inside of here are two evacuated tubes, protons going one way and the other way, and at 4 experiments they cross. And they're evacuated because the protons don't want to hit any particles or dust, because then they get lost.
So I understand there's less stuff in there than there is in parts of intergalactic space.
That's true, except this week, just so you know, just between you, me, and the lights, we were supposed to have collisions for the first time, and something was in there. I know.
What was it?
We have to burn it out. I think a piece of dust. Someone went in there after lunch with a...
Now, these protons you get are just in like a small canister, right? Don't you have you get the protons out of a small hydrogen canister?
So we get the protons from a bottle of hydrogen, and we just add an electron to the hydrogen. Hydrogen is a proton and an electron doing the...
It's not a lewd term, Melissa.
I don't have all my words. English isn't my first language. And so we add an electron. You need, when you accelerate things, it has to be a charged thing. You can't accelerate neutral things. So you either have to take off an electron or add an electron. Sometimes it's easier to add an electron. So then we accelerate that ion, and we get rid of the electrons later. You can just strip electrons easily.
Is this the Atlas instrument? Or?
So this is something we built for the NCAP. It's another magnetic toroid for the muon detector. Yeah. And this is CERN. It's so beautiful. And those are Europeans.
Oh, sorry.
They're also beautiful.
You're lowering this in?
So all of this happens deep down in a cavern, and there's just 2 holes for our experiment. You have to lower everything, including all the magnets. You have to lower them by cranes, which is really fun, but we're not allowed to do it. They have real people.
Union workers. Goes in there.
That's the other experiment.
Oh, we don't care about the other experiment and the Large Hadron Collider.
So, what's really interesting, and just so you know, is that we make 2 experiments, almost the same, totally different people, different personalities. And we do that at great expense so that if one of them finds something, the other one can say yes or no. And it's really smart to do it at the same time, even though it costs a lot of money, because otherwise you'd have to wait another 30 years, and we'd be dead. Yeah. I mean, I would be dead. So it's really good. Yeah.
So the instrument did indeed, parts of it exploded when it was first turned on, but then you came back, went up and running, and were you surprised at how quickly there was an announcement of a discovery? I mean, being on the team, being on the experimental team?
No, I wasn't surprised. I was surprised at how fast it got running. I think the CERN, this multi-country endeavor is unbelievable. I mean, much faster than us. If we did this thing on the prairie, yeah, we're cooler, but not as fast.
I mean, I don't think we've really set the stage enough for how important this was. I mean, really, it was the first target of this, $9 billion endeavor, was the Higgs. And do you feel it was as important as all that?
Yeah, it definitely was. I mean, it was a nice target in the sense that it was a no-lose situation. Either you're going to find the Higgs boson, and then you're going to say, we were on the right track. We've learned something important, fundamental about how nature works. You don't get that every day or even every year. This is, 1,000 years from now in the textbooks, they will still be talking about the Higgs boson. Or if they hadn't found it, it's more dramatic. It's sort of less helpful, but it's saying that nature is doing something very, very different than we've been thinking about, and we're at a loss, so we have to think harder. And thinking harder may or may not lead you to the right answer. So in this case, we realized that, 40-some years after the original idea, it was on the right track. We do understand that basic bit of nature.
Yeah, also, if you go to your funding agency and you say, I didn't find the Higgs boson,
can we have more money?
Really well. Yeah. They just don't get it.
Well, so 2 things. Well, I want to ask both of you. Were you more sort of satisfied that we found it, or disappointed? because it meant that we had sort of solved the puzzle so well that it was kind of depressing.
Well, I think that, it doesn't matter what my feelings are about finding the Higgs boson. It was fortunately it was there. I was happy that it was there because, sometimes you don't want it to be too easy, right? Like you don't want the first guess to be right because you want to learn something along the way. You want to be surprised by the data. We live in a universe that is accelerating that we discovered in 1998. That came as a surprise. We thought about the possibility, but we weren't really confident it was going to be there. The Higgs, we were pretty confident it was going to be there, but, we had been looking for it for decades. It was about time to do that and move on. You don't want to be, kept in suspense for too long.
Were you disappointed?
We were looking for it. Sorry. I just want to say that I hadn't discovered a particle since 1995, so I have feelings about it. I was pretty happy. And I have to say, I just want to tell you this. My students, when we found it, they were very, very excited. And then afterwards, they said, I don't want to work on the Higgs anymore. We already found it. Which is, that's how fast they move on these days. I still want to spend all my time poking that thing until I get a black hole in there.
We're going to talk about black holes. You tried to get a black hole in the collider. We'll talk about that in a second. Actually, why not just talk about it now? We're all over the place. Why not? There was a blackout.
I'm sorry, I didn't mean to. It's my fault. Just go ahead. I'll be good.
There was an attempt at an injunction to stop the LHC from turning on because there was a concern that it would make black holes that would consume the Earth. And the weird thing is, the first part of the sentence was okay with physicists. They were like, yeah, maybe it'll make black holes. But they weren't
that would be awesome.
concerned.
Come on,
let's
face
awesome.
it. Let's not play coy here. That would be awesome.
Yeah. But they just didn't agree with the second part of the sentence that it was likely to consume the Earth.
There's other planets.
No, actually, they did a lot. People did a lot of work. They took it pretty seriously, even though it doesn't sound like we could ever make a black hole. And usually when we make something, it decays almost immediately. And probably the black hole would too. But people took it very seriously. They wrote a 500,000-page report, I think.
Oh, yeah, they took it really seriously. It was like an environmental report. And one of the arguments is based on Stephen Hawking's result that black holes actually evaporate. As it happens, the smaller the black hole, the faster and hotter it would be. The faster it would evaporate and the hotter it would be. And so if you make a really tiny black hole at the LHC, presumably, if we're right, it would evaporate away effectively instantaneously, and it would be very hard to know that it was there. Presumably.
Well, it actually does lead us into the very important thing, because now that we have found the Higgs, that was what we thought we should find at the LHC. Beyond finding the Higgs, there's nothing that we put better than even money on finding. We think that we're very optimistic. Some of us are different levels of optimism. I'm optimistic we'll find something, but there's no one idea that I think has a better than 50-50 chance of being found. We're ready to find something new. The LHC is a special machine, not just because it's higher energy than ever before, but it's looking at a particular kind of energy where new things should be there, where we have physical reasons to expect we'll find new stuff. It may or may not work out that way. There's sort of the best possible thing where we make black holes or we learn something new about gravity or the theory of everything or string theory. But there's all sorts of other possibilities, and that's very exciting. We're waiting to see. We'll wait a week or two for them to get the dust out of the machine, but the next 5 years could be extraordinarily exciting time.
Before we go on to the new stuff, can you just offer an explanation of what would happen if the Higgs were to evaporate, if the Higgs wasn't there, if things were to change?
If we hadn't found the Higgs?
No.
Or...
I mean, I don't think we have a good sense yet of what it's doing for us. I mean, mathematically it makes things consistent, but that's very abstract. There's a physical story that might be helpful, I think.
There is. It's probably not helpful, but I will do my best. It's a long, weird story where it goes back to the fact that the particles out of which we're made, the electrons, the quarks, and so forth, they have this weird feature. They have spin. They're spinning either clockwise or counterclockwise in whatever direction they're moving in. And that's one weird property all by itself. But another one is they violate parity. That if you look at the rate at which reaction happens in particle physics, in the weak interactions, and you ask yourself, okay, what about the mirror image of that reaction? In the real world, the mirror image reaction happens at a different rate. It happens with a different speed. And this is something C.S. Wu at Columbia found back in the day, in the 1950s, and that was really weird, and no one had an explanation for it until Steven Weinberg came along in the 1960s.
Steven Weinberg will be here June 18th.
Yes, he's coming. I'm
Event number 4.
him. You should come to Steven Weinberg. And so what he realized was he had a brilliant theory that it explained why the weak interactions treat one thing versus the mirror image differently. The one little flaw in the theory was it predicted all of these particles out of which we're made, the electrons, the quarks, etc., were all massless. They had zero mass, which means they would move at the speed of light, which means that electrons would not fall into atoms. You would not have atoms. You would just have electrons moving through the universe at the speed of light. And that means you have no chemistry, you have no life. So it's a boring universe. It's not one you want to live in. And then he happened to be friends with the people who had the idea of the Higgs boson, and he realized, if these particles that I'm thinking about feel the influence of this field filling all of space, they will get mass. I can both explain the mirror image symmetry breaking and the mass of the particles at the same time. All I have to do is give myself an invisible energy field filling all of space. So without that Higgs field, the universe would be a dramatically different place than we have right now. And as Janna's alluding to, the Higgs field is different than everything else because it has a non-zero value in empty space. We talk about fields filling space, but out there in interstellar space, most of the fields are just zero. They're sitting quietly. The Higgs has a whopping big value. And if that value changed, everything would change. All the masses of all these particles would change, chemistry would change, everything would blow up, life itself would be impossible. So for the next 2 billion years, we're safe, but don't, plan beyond that because we just can't really guarantee anything.
So I just want to say, from the experimentalist point of view, we collided the particles at 8 TeV in the center of mass up to 2 years ago, and now we're going to collide them at 13 TeV. And independent of theory, it's going to be interesting because we're at a frontier. So we're just sitting on our horses with our cowboy boots and waiting with lassos.
How long have you been working on this experiment? You've been that wasn't meant to be a personal question.
This experiment, the previous experiment, 32 years. This experiment, 15 years. That makes me almost too old to be believed. But they overlapped.
So you're building this they overlap. You're building this tremendous machine. It's been called the most complicated, biggest machine ever built by humans. You must have believed something about the theory of the Higgs, of these crazy theorists pontificating about this.
It's complicated. I mean, you listen to the theorists and then you try and forget what they say so that you won't be biased, because we don't like being biased. So you look at the theorists, you listen to them, you love them in their own way. And then I remember looking back, I was just throwing away stuff in my office and looking back at acetate that we used to use to give talks in which I said Higgs schmigs. Of course, when we found the Higgs, I was very happy. So it's a complicated relationship. Theorists often think experimentalists are just sort of pigs that snort things from the ground.
Well, I've never had
and I've
such
always,
a thought.
Oh, no, absolutely. You know this story, right? The truffle.
No.
Yes.
But I'm fascinated.
So a very famous physicist, I won't mention his name, who came up with grand unified theories, wrote that theorists are like truffle farmers, and experimentalists are like the pigs. So the truffle farmers take their pigs to the right area, and then the pigs snort around. So for a really long time, I was a bad pig, like, hey, I'm not doing what you tell me, farmer. And then just lately, I've come to terms with how much I am a pig.
And how good those truffles are.
And how good it feels to be that pig. I own my pigness.
So your thinking is more, let's just smash these things together as hard as possible and get to the highest energies that we have ever been able to attain, by human brute force.
I have to take, yes, I have that part of me, and then the other part, which is you look at the theory, it's beautiful. I mean, it's incredibly simple. I don't know if Sean can talk about that, but this is probably the simplest solution you could imagine to this problem theoretically. It's absolutely beautiful. I mean, you just have to lie down.
No, it's lovely because it looks like such a mess from here, right? The world looks so complicated. And it looks like, even to particle physicists for a long time, they kept generating new particles that were unwanted. Robbie famously said, who ordered that? Was that the muon?
The muon,
The muon. And, it's detected by this thing. There was this plethora of junk, and that is not what the theoretical physicist wants, right? The philosophy and the hope is that there's this aesthetic simplicity underlying it all, and it will all pull together, and it'll all sort of be one simple thing. And the Higgs plays a really important part in making that pull together, so that you can see from a distance it's just actually one beautiful, simple, symmetric system. Would that be fair to say?
It's not one. But...
Well, the electroweak theory, you would say, or at least, unless...
How many parameters are there?
Well, that's
19,
21, I don't know.
I mean, it's weird true. Because, I think exactly like Janna said, it's this the standard model of particle physics. On the one hand, it would fit on a T-shirt if the T-shirt, supported very small fonts. There's a lot of lines to the equations if you're really writing down everything. So in that sense, it's kind of ugly. There's muons and there's tau leptons, and the neutrinos are doing weird things, and why do they have the masses they do? And we don't know the explanation for anything. So there's a lot of, we do suspect there is order underlying all this apparent chaos, and that's what a theorist is trying to propose models for. But I think that what Melissa was getting at earlier is that the Higgs itself is like the simplest version of the thing that can do the Higgs's job. The Higgs field that was first proposed in the early 1960s, certainly we tried to do better than that, in the decades after that. We tried to make better models that sort of didn't have some of the arbitrariness, more complicated models, and none of those were right. It was the first simple model that turns out to be what shows up at the LHC.
So I want to ask, what now? So I know you can keep looking at the Higgs and finding its details, but there must be something... I mean, there's another reason why the LHC is turning on at even higher energies and is going full throttle for the full scale height of the instrument.
So we're doing it because we can, and we will study the Higgs, and we're getting a lot of money to do that. But we will also look for dark matter, and we will also look for supersymmetry. A whole bunch of new particles that probably aren't there.
Tell people what dark matter is.
Dark matter. Dark matter is this stuff that they've seen in out there in the sky, in the universe, that doesn't interact with light, doesn't give off light, doesn't eat light, but it bends light because it's got a gravitational field, so it's massive. So we're trying to figure out what kind of particle that is. There's a whole bunch of people underground all over the world looking for this. Going underground, we could talk about that, but it's a good place to go. There's a wind of dark matter going through the Earth, and we might be able to see it, but we also might be able to see it in the accelerator. So we're looking for that.
The dark matter is also a huge amount of what we know to exist in the universe. So what's stunning about it is that we're just a tiny bit of stuff, right? The protons, you, me, the Earth, everything we've ever seen basically in the universe is less than 5% of what makes up the universe. And by far, the bulk is in something called dark energy, and there's, 4% in this dark matter. And we only call it dark matter because we don't know what else to call it.
But we're the 1%.
True.
Occupy the universe, yes. The existence of this dark matter is the very, very strong evidence that we're nowhere near done yet in finding particles, even particles that stick around. So, you could imagine that we lived in a universe where all the particles that lasted more than a femtosecond we had already found. right? There's the electrons, there's the protons, there's the neutrons. We found them, they're in our detectors, and you could imagine a world in which there's just nothing more to find that sticks around like that. But we know that's not our world, because there's all this other stuff out there. Most of the mass in the universe is dark. It's not any of the particles in the standard model of particle physics. So that sort of nightmarish scenario for physicists, where it's going to be very hard to find new things, is probably not our universe. There's something very blatantly out there. Whether we'll be able to find it, we don't know. We're looking at the LHC, like Melissa says. We're looking underground. We're looking at the sky to see whether or not the dark matter might be doing something interesting, like annihilating and giving off high-energy photons or something like that. But we know it's there. We can make maps of it. We can see its effects on other stuff in the universe. So, we are the Christmas lights on the tree of the universe. We're the part that shines, but we're not most of the stuff there. So this journey is very far from completed.
Do you think that the Higgs is going to be the portal to the dark matter? I mean, that is part of the hope, that the Higgs wasn't, okay, we sealed that one up, now where's the dark matter? Like, they're disconnected phenomena.
Yeah, so that is, like you say, that is the hope. The Higgs boson is special for many reasons. It's the only particle like it that we have ever found. It's the only particle that we think, as far as we know, is fundamental, is not made of other particles, that does not have any spin all by itself, for example. And for these technical specialness reasons, the Higgs is kind of more sociable than other particles. It's easier for the Higgs boson to talk to the dark matter than for the electron to talk to the dark matter. So in terms of theorists writing down the space of possibilities, there's all sorts of tantalizing possibilities for the dark matter to be interesting in and of itself. Maybe we talk about the dark matter particle. Maybe there's 23 different kinds of dark matter particles, and there's like dark atoms and dark chemistry. We don't know these things. We know it's very different than ours, but maybe it's complex. Maybe it talks to us. Maybe there's a whole new dark physics that'll keep us occupied for the next 250 years.
What is there, something like one dark matter particle for a cup of coffee or something like that? For a
It
cup
depends.
of coffee
Yeah, that's
volume
right.
of the universe.
For a very natural, unsurprising value of the mass of the dark matter, which we don't know, but if you sort of guess at it, then yeah, it would be very natural if in any region of space this big, there's on average one dark matter particle. But they're moving at hundreds
as you
of
said,
kilometers.
they're flushing through us like a wind.
Here's the thing. Supposing the Higgs decays to two dark matter particles, what do you see?
That was exactly my next question.
You see nothing. So that's why it's really, really hard, because it's hard to look for nothing completely. Sometimes you say, oh, there's nothing. So you look at all the Higgs decays into other things and you say, well, it's not enough. Something's missing. But to see nothing.
I see nothing all the time. I don't see why this is such a big challenge. Every experiment I've done, I have seen nothing.
That's deep, but
So what are you going to look for? You're going to continue to
we're going to look
smash
for
particles.
nothing. We're definitely looking for nothing because we rock. We can look for nothing, especially if dark matter is created across from something else. So it's created with something else, and we look to see something and then nothing, and the nothing is missing energy. It's a really beautiful thing. That's actually how we see neutrinos as well. Something that's not there, like the man on the stair.
So what about neutrinos? Do you think there's any connection? You said it's like neutrinos. Neutrinos are these particles that do fit into the standard model, but are dark. I mean, they are an example of dark matter. We just know that the standard model neutrinos can't be responsible for the amount of dark matter we see. So do you think there are other neutrinos that just are outliers?
People say there are sterile neutrinos.
There's a lot of sexual metaphors in physics.
Which is sad. Neutrinos...
They're also impotent neutrinos, and potent ones. I think impotent ones are the same as sterile ones, though. I think that terminology faded. I'm very sorry to have brought it back up.
I think you're reading very different physics papers than I'm reading.
Yes, neutrinos morph into each other, the three different types of neutrinos, but there can be sterile neutrinos. People are looking for them right now. I have a friend, not really a friend.
This is being recorded, Melissa.
Not anymore.
I'm just kidding. No, people are looking for, there's a massive amount of people looking for sterile neutrinos as well, and just measuring everything about neutrinos. But I don't know where the dark matter is going to come from. It's going to be very interesting. And if there's anybody young here or coming back in the next life, there's still work to do.
Do you think there will still be work to do? Are you concerned that we will ever build another accelerator, or we will ever build another instrument like this? Is this the last of its kind, do you think?
Absolutely not. We're just going to be smarter. Instead of a 27-kilometer radius accelerator, we're going to build a 3-centimeter radius accelerator with the same energy. And everyone is going to have one in their house. It's like the computer. So every person can make their little black hole and stroke it.
That actually sounds totally irresponsible.
Well,
I mean, people don't know how to use their VCRs still.
VCR? What are you talking
What? Did she just say that?
VCR? No, I mean...
So, actually, you mentioned supersymmetry, and I kind of cut you off to talk about the dark matter, but it's a very esoteric issue that it would be worth mentioning. So, do you want to try discussing supersymmetry?
So there's lots of symmetries of different kinds in physics. In fact, all we do really is study the symmetry of the universe, the symmetry of space-time. If we get... That's pretty much all we do all day. And one possible symmetry is that, Sean mentioned spin, that for every spin 1/2 particle, called a fermion, there will be a partner, which is spin 1. So somehow we'll rotate in this space from spin 1/2 to spin 1, and there'll be the same thing. You know how when you rotate, nothing changes? Well, yeah, you see different things. No. Do you rotate a circle? So theorists for a long time, especially string theorists, have thought there is supersymmetry, that for the electron there's a partner called the selectron, and it should have the same mass and everything. And for every particle that we have, there should be a partner, a super partner. And we haven't found any. So if there is a selectron, it's not the mass of the electron, it's like
Bigger.
As Sean would say, way bigger. And we keep looking every day. Some of my friends look for these super partners, and they don't find them. And the theorists are getting sad.
Now, could they also be responsible for the dark matter as well? Some of these particles?
Yeah. Some of the supersymmetric particles could. Some of the ones, Sean can tell you which ones exactly, because they have names I don't like to say. But it is, sociologically, it's kind of sad because these incredibly brilliant string theorists are now getting sadder and sadder that there's no supersymmetry, although they won't give it up. So in the end, it may be super, but there won't be any symmetry.
Well, in some sense, like everybody else, physicists are always fighting the last war. And we had this tremendous amount of success in the 50s, 60s, 70s in coming up with the right models of how the universe works by thinking more and more symmetries that we could impose on nature. And it worked over and over again, so that's what we're still trying to do, as Melissa says. And maybe that's not the way nature works next. We could have found supersymmetry already, either at the LHC or in various other experiments. That's not to say that we won't. Maybe a year from now, we'll be back here and discussing the discovery of supersymmetry, but maybe not. And, it's a theoretically compelling thing, but nature may or may not work that way. And maybe if we don't find it, we were lucky enough to find the Higgs. If we had not, theorists would have thought harder. It would be fortunate if we found supersymmetry. If we don't, theorists are going to have to think harder. They might need to think outside their little symmetric boxes and come up with something very different. There's clues, right? There's a weird thing because the Higgs boson, even though it does its job, its mass is way smaller than it should be. This field that is filling empty space has an energy. That energy is way smaller than it should be. Gravity doesn't really fit in to the whole picture. So we know that we're not, done. We know that maybe you might need a whole breakthrough. You might not need just like another spin, as it were, on what we already know, but a different kind of theory entirely.
If I could just throw in a little background, one of the reasons why people got excited about string theory references something Sean said in the beginning is that we keep trying to unify everything together. The aspiration of theoretical physics for a long time has been to effectively have one mathematical sentence that describes all of the fundamental forces, and string theory seems to be able to do what no other theory had ever been able to do, which is include gravity. So string theory is a description where when you look at elementary particles, close enough, you realize that they're not particles at all, but little loops of string, and that everything is really a loop of string, and that we're all just, all the different particles that Melissa's discovering at these colliders are actually just playing different notes in some sense on the same fundamental string. The story gets much more complicated now. String theory requires extra spatial dimensions, which I think is something, now that we're pushing to the scientific controversies, these are things we take seriously now, that the universe has extra spatial dimensions, that maybe Melissa will be somebody who finds them at the Large Hadron Collider. And I want to know if you ever took that proposition seriously, because there was a lot of talk for a while about this.
I looked for them.
Personally?
I just want to tell you, if you have another spatial dimension and you have a collision and one of the particles goes in the extra spatial dimension, you know what you have? Nothing. You have missing energy. So I look for missing energy all the time. So I have looked. I haven't found it yet, but
no extra spatial dimensions. That's so depressing.
I know. I love the extra spatial
I have
dimensions.
a theory about extra spatial dimensions and dark energy. I want to try on you guys later. We'll do that over drinks. So it was very depressing to me.
We won't tell you guys about that.
It's a good theory. It's a good theory. It was very depressing to me that there. I mean, I did not actually expect you would find it. This is stuff that no, the extra spatial dimensions, if indeed they exist. But one of the strange properties would be that the extra dimensions are small, right? We think that they're small if they exist. Small in the sense of the round part of a straw being small, it's hard to stick your hand in those extra directions. And so only if you go to a collider and you make very high energy, very tiny particles, very energetically, can you lose something down that sink. So you don't, when your keys are missing, they're not in the extra dimension, generally speaking. Only very high energy particles are. So there was some hope that they'd be big enough to fit particles coming from the LHC. And that's actually quite big. Do you remember how big they were saying the extra dimensions would have to be? Well, millimeter, sub-millimeter. Literally, sub-millimeter size.
About a millimeter, yeah. So, it depends on how many you got. And if there were precisely 2 extra dimensions that were what we call large, which is larger than, the sub-microscopic scale, 1 millimeter across, or maybe 1/10 of a millimeter, was like the sweet spot where everything would work out. And so those could have been found, and we didn't find them. Yeah.
Now, does it mean that there are not extra spatial dimensions?
No, it's very easy to have the extra spatial dimensions be much smaller than that, and sort of not helping us with all these puzzles that I was mentioning before.
So I just want to make a note here, which I think is fascinating. It's not my idea, so it's fascinating. But theorists are wonderful things. They just come up with wonderful, clever ideas, and it doesn't really matter whether they have anything to do with reality. Because just thinking about the ideas actually stimulates experimentalists to make experiments. So there's a whole bunch of experiments that were on gravity at very short distances were stimulated by these clever ideas about extra dimensions. There probably, and don't quote me, are no extra dimensions. But the fact that theorists constantly come up with clever ideas means that, science goes on in different ways.
No, so this is really, I love this because you really think that this is just way out there stuff to be talking about. It's cute. It's cute that people are doing that with their pen and paper, but it's not really something, you certainly wouldn't build the LHC just to find the extra.
I'd build the LHC
for anything.
For any reason. they gave me the money.
But Sean, do you think the extra dimensions are frivolous like this, or do you think that they're like the Higgs?
I didn't say frivolous.
Melissa Franklin thinks they're frivolous.
I work with people. I didn't say frivolous. I said clever. I think if you.
Well, let's just put it this way: the Higgs was ignored. The Higgs was ignored for a long time as just this ridiculous offering that was clearly probably not right, and it was very contentious, and nobody really paid that much attention. Do you think that the extra spatial dimensions one day will fall into that category that, okay, it sounded ridiculous, people, but, there they are, we found them?
I actually am pretty darn agnostic about that. I think that, the arguments in favor of the extra dimensions are really pretty good arguments. We talked about string theory, and I think it's very legitimate for the person on the street, even the PhD physicist on the street who is not a string theorist, to go, why in the world are you exerting so much intellectual effort thinking about this theory that has 0 empirical support so far? And there is an answer to that. I mean, they were thinking about string theory originally back in the 60s and 70s, and there was almost no intellectual effort spent on it. There were like a couple people who thought it was a cool idea. And they just kept, those couple people kept plugging along, asking what would this theory be like? And they kept predicting the existence of gravity. And that annoyed them because they were not trying to predict the existence of gravity. But then at some point, a couple of people, including my Caltech colleague John Schwartz, said, wait a minute, gravity exists. Maybe that's a good thing to be predicting. And suddenly it became a theory of gravity. And when they, just like Gerard de 't Hooft in the 70s, showing that Weinberg's theory made mathematical sense, in the 80s we realized that string theory also made mathematical sense, and the theorists became very excited. That does not mean it's right. There's a whole bunch of theories that are equally interesting as string theory, but just don't have that nice sort of fitting together, making everything work property. One of them could be right, where maybe we're just not clever enough to make it work. So when it comes to quantum mechanics, gravity, theories of everything, I do not think that we are smart enough to have the right ideas yet.
And just to emphasize this, it only makes mathematical sense with the extra spatial dimensions.
That is right. So that is one of the big motivations. But there's a more primitive motivation, which is just exactly 100 years ago, Einstein taught us that space and time are dynamical. They're curved. They can move around. If you believe that general relativity is true, you can go from a universe with three-dimensional space, which we have right now, to a universe with 2 dimensions of space. The dimensions of space is not a conserved number in general relativity. So there's nothing special about 3 dimensions of space. In some very broad sense, it'd be very surprising if there weren't more dimensions out there to be found.
My favorite theory ever came shortly after Einstein proposes general relativity, and some people start asking, why 3? And some theorists started to look at models of extra spatial dimensions with only gravity. That's the entire theory of the universe, gravity. There's no matter, there's nothing else in it. And they realized that some of those gravitational modes in the extra spatial directions look a lot like light, and that maybe there could be a unified theory that's only gravity in some higher dimensional space. And it just gives the illusion in this 4-dimensional world, when those other dimensions are wrapped up, to be matter forces and gravity as well. It's the most stunning theory.
And it might be wrong, but, it's great to give to our experimental friends for their grant proposals. So spurs new efforts.
So you said maybe we're not smart enough. That's sort of an idea of Weinberg, that we're sort of dog-like compared to the problems we're... Do you
There's
think
a lot of animal metaphors going on today?
If there were more women in physics, do you think maybe that would...
Yes, I do. And I've tried. But, I think that the more talent we get in physics, the better. On the other hand, I'm smart enough to recognize there are other things worth doing than physics. So the more talent we have everywhere, the better.
So one thing we haven't gotten into yet... I don't know, I'm breezing past that. It is the dark energy. We haven't talked about the dark energy. So I said 25%, a little less than that, is in the dark matter. And the rest, by far the bulk, is in the dark energy, which again is just a name we give to something we have no idea what it is, but it is the thing driving the universe to expand at an accelerated rate. Is there any hope that this is connected to the goddamn particle?
There's hope. My suspicion, sort of my theoretical guess, which may or may not be right, is just that as interesting as the dark matter is, the dark energy is boring. The dark energy is just the energy of empty space. It's not changing with time. It's the same amount everywhere. I hope that's wrong. It's much more interesting to be changing all over the place. It looks kind of vanilla and boring. But it might be temporary. It might be that if the Higgs boson changes its value in empty space, then the dark energy would change very dramatically, and as we were talking about, the universe would itself be a very, very different place. So there absolutely could be a connection. We don't know what it would be yet, but we have to wait to be surprised by some data, I think.
I mean, what do you think, Melissa? You think it's just an accident that we're coming in these kinds of proportions of dark energy, dark matter, that they're not connected, they're totally disparate?
I don't really know anything about dark energy except the other fields of physics that are taking our money. No, I don't know anything. I mean, I know what it is, but I have no feel for it. I don't know how to look for it myself. I know how other people are, using.
I mean, I think that's generally true. I mean, it is, in some sense, much more mysterious than the dark matter, which at least we have candidates for dark matter that exist. Yeah, like neutrinos. They exist. We've never seen anything like
dark matter.
Dark energy.
We have ideas. Dark energy, it's astronomers.
Well, no, I think we have very good, we have a much better idea in some sense, a much better idea in the sense of a model for what the dark energy is. It's the vacuum energy. It's the energy of empty space. It's a very simple idea that fits all the data perfectly. It's 98 years old. Einstein came up with it. We are hoping that it's wrong because it's so boring, but it could be right.
Well, so I don't have a watch. I'm embarrassed to say I'm very irresponsible, so I'm going to ask Shel my time is. So before I want to go into one more topic before we open up for questions, and that is about the significance of this discovery for our future. You said if the Higgs disappears, it's a very different world. It's an untenable world. It's certainly not the chemistry and the evolutionary biology that we've experienced here on Earth if the Higgs never existed. But what if it changes? Do you think that there is a future in which this Higgs field that permeates all of space just sort of drifts away, slips to another value, vanishes, isn't there anymore, and that changes the world that we live in?
I think that it's extremely unlikely that it either slips away or vanishes. It could grow. You have two different numbers, so this is why it's a little bit subtle. There's one number which is the value of the Higgs field in empty space, and there's another number which is the energy contained in that value. And so the way that it works out is if the Higgs field were at zero value, it would have a tremendously higher energy in empty space. The value it actually has is the lowest energy as far as we know that it could take on. It might be the case that there's a much larger value the Higgs could take. Think of sort of the hills and valleys in a landscape. Maybe there's another valley over the way where the energy of the Higgs would be much lower, but we're protected by by some mountain range. And so it's not going to slip over there. There could be some explosive transition that takes us from where we are to over there that would dramatically change the face of the universe. No one would survive the cataclysm to write about it.
We would literally explode.
Yeah.
Our atoms would just sort of puff out and explode.
That is correct, yes.
Something to look forward to.
Or collapse into black holes. Something bad. Bad things would happen, but we can't stop it from happening. There's no...
Well, so is it possible, you're describing it as over there. Is it possible that it's literally over there? That there's another region of space and time where the Higgs has a different value than it does in the universe that we observe?
Yeah, absolutely. The history of science has been one of Copernican revolutions, right? Like, we're not that special, we're not that central, we're not that unique. We live in a universe that it's only been 13.8 billion years since the Big Bang. And we look at the universe using light, which moves at the speed of light, which is a finite number. So we can't see the whole universe. So the universe, the part of it we see, all looks the same. But it's very, very possible that beyond what we can possibly see, the universe looks like a very different place. Maybe different values of the Higgs boson, maybe different numbers of dimensions of space, different kinds of particles and forces. That may or may not be a relevant thing to keep in mind when we're trying to explain the universe that we do see.
And can we just call it the multiverse? Just call it by
name?
We
can call it the multiverse. We do call it the multiverse, even though we shouldn't because it's just one big universe.
It's a megaverse.
We call it the multiverse. Yeah.
Do you think that this is something that you would be
unlikely.
concerned? Yeah. Unlikely that there are other patches of space-time which have experienced Big Bangs, or unlikely that the Higgs has different values in different parts of the universe?
Yeah, I think everything we've learned so far is that physics is the same everywhere. So it would be interesting, but weird, I guess. This is really kind of too deep for me. Sorry.
Well, no, actually, this is a simple question.
Actually, I'm feeling sad.
I'm really curious about this. Do you think that our Big Bang was the only one? That when we look back roughly 14 billion years and we see the light left over from this tremendously energetic event, which seems to have launched this whole ridiculous conversation that we're having, which began with initial conditions and the origin of the universe, do you think it was the only time it ever happened? It was the only one?
No. I'm afraid to say no. But I also think Philip K. Dick was a reasonable person. Sorry, he's a science fiction writer. I think every time we discover a particle, I think, are we just discovering it in a dream? Because the theorists have convinced us that it's there. That's sort of what I...
Are you surprised when you genuinely find them? It is
so
surprised?
exciting to find a particle, I have to say. Even though it happens in slow motion over many months, you don't even know you've discovered it. Kind of exciting, especially because there's 2 experiments, and you don't know what the other people have. So you have almost something, and they have almost something. And only the people who are sleeping together really know. which, by the way, is a lot. Because it's Europe. And, a lot of things happen.
So there is a moment when you turn the machine on, but there isn't really a moment when you look and go, aha, there's the Higgs.
There's no aha.
Mm-hmm.
Yeah.
So at first you just sort of hear that there's a hint. And when was the moment when you got really excited about the Higgs?
Since I don't like sex, I learned at that
and I was
press
worried
conference.
about asking a personal question.
That's right. At the press conference, that's when it really. That was really nice. I mean, of course, you hear hints and everything, but when you actually see the other experiments' data, and you go, "Oh, we weren't totally wrong." That was really exciting.
So the announcement was made on July 4th in Europe. It was like 3 or 4 in the morning in the States, and I stayed up and watched it, on some live streaming. And it was the most hysterical announcement from the outside because they were like, "And we see an excess in the photon channel, 125 GeV."
Why is that funny?
And everyone's like, so people start, Higgs himself, the man after whom the mechanism is named, starts to well up. It's really just a tremendous event. But they would not say, we discovered the Higgs.
Well, we don't know we discovered the Higgs, and we don't know it's the only Higgs. When we turn on, which could be any day now, after the dust settles, dust is big these days in physics, we'll find out there could be more Higgses. It could not decay. We haven't measured almost anything about it. So the last thing I measured about the Higgs, we only had 20 Higgs decays. So it could be weirder than we think.
So just before we open up to questions, do you have a takeaway message you would want? Because this was a pretty chewy conversation. There are a lot of ideas flowing around. Is there one you want to cut through and impress upon people? You can say no.
I've never said no to that question. That's not. I think that this is a historic moment, the finding the Higgs. It's a historic moment, both in the sense that it's the completion of a certain project and the beginning of a next project. And by project, I don't mean like some particular experiment. I mean a whole intellectual endeavor. Everything in this room that you can see with your eyes and touch with your fingers and so forth is made of particles that people like Melissa have discovered in experiments. We know what all the particles are that make up you and me and this table. And we now have a theory that explains how these particles behave, that we've sort of put all the pieces together. We know it's not the theory of everything, because it doesn't explain the dark matter, the Big Bang, the black holes. But here in the room, we actually understand that. And that's, we've been working at this for thousands of years, and now we have it.
Melissa?
Why don't you come to CERN and visit us? It has a kind of nice place you can see things. And it's kind of exciting. It's worth it. I mean, where are you going to go? Yeah, and also buy Sean's book. It's really good.
Oh, yeah. We will have books for sale.
And encourage Melissa to write a book.
Yeah, that's...
And I my one takeaway message is Steven Weinberg, who came up in the conversation today, the brilliant Nobel Prize-winning physicist who really is just very widely admired, a wonderful person, will be here for a Scientific Controversies event coming up in June. We're really excited to have him, so please look out for that. And the topic will be, can we explain the world? And it'll be just, it'll be like really light, really superficial.